capturing. Let me just go ahead and do it right now. Okay, so these two things, when you see them together on the same chain with this reagent, it is just going to glue them together. Okay, it's going to be also a Markovnikov addition. So what's going to happen is that the bonds are going to be formed up to right here, because this is a Markovnikov spot, right? Anything after that would be outside the ring. Okay, so let's see. Let's add it here. Anything after will end up outside the ring. Okay. Let's see. So when I have this reagent, and I'll get this product here. Okay. So these are stuff that you are probably gonna see as predicting the product kind of questions. It's really, really common. So at least now you guys should have an idea of what's happening. Okay. The next thing I want to talk about is this right here. Yeah, you could put AC2O as well, Ariel. Solvents I'm not too concerned about. It's just more of like identifying the main reagent. Okay, so can anyone tell me what this synthesis is called? Yeah, it's called the Gabriel synthesis, right? And why do we need the Gabriel synthesis for? We need it because what happened if we use if we try to use ammonia instead to add an R group to ammonia? It will overalkylate, right? So we use this to prevent overalkylation. With ammonia. Okay, so what you have, for example, is that if they give you something like this, okay, and then step 1 is the same. Step 2, I have, sorry, it will be the same thing. Hang on. Let me see. Right, what I get is I just form NH2. Okay, so remember that this is a 3-step process. And yeah, I believe Dr. Yamalina did talk about this mechanism last week. Okay, so if you added, for example, if you had, let me think of an example. I can't remember any, like exactly what happens right now because, well, this has been quite a while for me. So let's say I had this, right? Something like that. What happens is that I'm not going to get this product. Instead, I'm going to get this product here. Right? It will over-alkylate. So we cannot do that with Gabriel synthesis because Gabriel synthesis, it controls what I get. I'm only going to get the desired product, and I'm not going to end up with the case of over-alkylating an ammonia, the nitrogen atom. Okay. All right. The next thing is mirror, mirror on the wall, who's the fairest one of all? Why? Because we have silver oxide. Okay, when you see this, know that it's a Hofmann elimination. Okay, and usually we make anti-Markovnikov, right, product. So let's see. All right, if I had this here. Okay, NH2. What I'll get is this product here. Okay, and that's a cyclohexane, by the way. It's not a square. Do take note. Okay, so if I had this material here and I made a Hoffman elimination, what I can do after that is to, well, I'm sure you guys know some of your alkenes already, right? So if what I have right now, this amine right here is Markovnikov, and if I wanted to make it anti-Markovnikov, okay, what I'm gonna do is that, for example, if I wanted this product, okay, so I changed the Markovnikov to the anti-Markovnikov position. This is what I'm gonna do, okay? After I have my elimination, I'm gonna get my Hoffman alkene, right? So I can do BH3 and THF, and then step 2, hydrogen peroxide and NaOH. Now, those who were in my Orgo 1 class, who is this guy? If I called him 9BBN, do you remember who 9BBN is? Great, yeah, it's Batman, right? Batman and Robin. They give the anti-Markovnikov alcohol products, right? So for those who are not sure of why I'm calling it Batman, because 9BBN looks like this, right? I mean, it just reminded me of Batman. And what we do is to hydroborate it, and then after that, oxidize it into an alcohol. Then what am I gonna do? I'm gonna oxidize it so that I get, I'll show you what happens at each step here. Again, height, correct? And then step 4, I can add my amine group, NH2 or whatever I'm gonna add, right? And then after that, I can just reduce the bond down into a single bond here. Okay, so this would give me the products here. This is a really sneaky way of asking how I can convert a Markovnikov to anti-Markovnikov. You would have to find the Hoffman intermediate, and this is exactly what you do. You have methyl iodide and silver oxide and heat. Okay. All right, this one here. Well, it's okay. Let me just write it down first. Okay, so let's consider if I had this molecule here. Okay, and I sent it through this step here. So I'm gonna send it through this is step 1, okay? Step 1. Now you need to start off with an acid chloride, okay? And if you had this product here, what you're gonna get is a Weinreb amide. Okay. And it's usually an intermediate that precedes a Grignard reaction. So if you see this product here, the first thing you want to look out for is if there's a Grignard lying around somewhere. All right, but when you did alcohols with Grignard, when you did Grignard with usually like different R groups, you would usually get alcohols, right? But when you have a Weinreb amide intermediate, you would end up getting a ketone. Okay, so you would have a carbonyl present, and not, so we'll synthesize a carbonyl, and not an alcohol. So please take note of that as well. Because of this vine wrap amide here. So step 2, if I take my vine wrap amide, and then I finish it off with step 2, step 3, and I'll just end up with the R group that I wanted to put on in the first place. See? And I get a ketone. Please don't write stuff like this. This is wrong. Okay? It's not an alcohol, it's a ketone. All right. Let's try some questions just to warm yourselves up. These are some of the, I compiled like some old exam questions for us to work on together. So let's see how if we can apply what we just learned, okay? Who is this basic girl here? What does she do? She's a strong base, right? If it's a strong base, I will form, yes, the kinetic analog. Exactly, so I will get this. And we're going to consider all these a lot more in detail in a bit. Okay, now the next thing I do is to add on whatever this whole business here is, right? So I can do this. Let's see. Well, I'll talk about why we have this stereochemistry later, but and then the last step is to just make it into an alcohol, right? So this is something that we're gonna do in detail later. Don't worry, because I have a small R group here, so I know I'm gonna get the anti-product, and then I get alcohol here, right? So this is the enolate chemistry part. Okay, what about number 2? What is number 2 doing here? The first step is, well, it looks like a Gabriel thing to me, right? It adds an NH2, so I'm going to replace bromine with NH2 here. Okay, good. And then step 3, who's that person again? What does this reaction do? It attacks the anti or Markovnikov site. Yes, good. You guys remember it's a Markovnikov site. So I'm going to cyclicize it, and it becomes a ring, right? So what I get is right here. Good. It's number 1 and 2. They make the intermediate here. So 1, 2, and then step 3. Okay, likewise, this is step 1, step 2, step 3. Okay, number 3. So want to make a guess? What happens? Write it out. Yeah, exactly. So I convert the ketone into this NH2. Well, because I have hydrogen in there, right? Oh, I'm sorry. NH3. I realized I forgot a reagent here. Okay, I have this here, and then what happens after? Exactly, Zaki, you're right. We are gonna make a double bond because we have silver oxide in here. Let me just see. I wanna make it a little bit clearer in my reagent front. Let me just go ahead and do this instead. Okay, so we know step 1 gives us this product here. Okay, and then we can, yeah, so I guess that's where I kind of missed out on the review sheet. So please go ahead and add this part here. And what we have after that, we can go ahead and do our Hoffman elimination, right? Because I have methyl iodide, silver oxide, and heat. So what I get is this product here with a positive charge, and then iodine just kind of floats around in solution. What I get at the end is a Hoffman alkene. Yes, I think NH3 and hydrogen. If you have hydrogen in there, it should do the same thing. Okay, step 4, number 4, let's just keep it for later until the end of, until we finish everything. Okay, I'm sorry, let me just silence my phone. All right. And then once we finish talking about enolate chemistry, we'll come back and finish off that question. Okay, I just want to remind you that exam 1 and 2 material are still fair game, so please remember at least what's happening. This is a Vidic reaction, right? So what does a Vidic reaction do? It takes a ketone and it converts it into an olefin. So when you have this, you're gonna end up with this here, isopropyl. Okay. Stuff like that. Can you predict the reagents for me for this step, this reaction, number 2? Good. Yep, and that's exactly what we're going to use. MCPBA and dichloromethane. Don't forget this is the Baeyer-Villiger oxidation. All right, and then the last one, Dibble. Fantastic. Good. You guys are, I think you guys are pretty good so far. All right. What about this one here, number 4? Do I reduce all double bonds? Only the one on the left, exactly. Anything above a secondary alkene would not get reduced, right? So remember that Wilkinson's catalyst is selective. All right. And of course, don't forget the strengths of your ketone. I'm just gonna say it really quickly. If I had methanol in water or an acid, I'll get an acetal. Stuff like that. Don't forget. And then if I want to go back, I can put acid or water, right? Don't forget, if you need to protect your ketone as well, make sure you know how to protect your ketones if you have to. Okay, what about, yeah, the last one you guys got it right there is sodium cyanoborohydride. in acetic acid. Good. Okay, so stuff like that, don't let it get to you. I'm sure you guys, might get flustered, but take it easy. Okay, you got this. All right. What about? Yeah. What about number 7? What does number 7 do? Are you sure? Yeah. For a moment, I thought like, oh shoot, am I wrong? But no, yeah, it's a cyanide. Okay. See, be careful. Be very careful, and this is why I know I deliberately put this here, because I do want to talk about the mechanism. This is exactly the same problem I got last semester with my students as well. Okay, it's not, take note, this is a amide. So if I put in thionyl chloride, I will get a nitrile. In fact, I don't have this. I'm adding too many carbons, right? Okay, so let's look at the mechanism, just to refresh on your memory. Okay, so I'm starting with this, and all right. So the first thing that thionyl chloride is gonna, it's not thionyl chloride, sorry. Don't forget that amides have a lone pair. Oh wait, was this part of your second exam? Okay. So since it's there already, I'm just gonna copy and paste a mechanism on there. I'm just more concerned that you guys know what it does, and since it's already on your second exam, then I'm not gonna go through the mechanism in detail. All right. I'm just gonna move on so that we can spend more time on alpha carbon chemistry. Okay. Just a show of hands here. Who is struggling with this chapter? And honestly, the only reason I'm doing this is like I'm focusing so much is because I notice students tend to like get it mixed up. Well, 6, 7, 8, 9, 10. Okay, yeah. So all right, all hands down. Thank you for that. So if you're already familiar with alpha carbon, then you can just stay on and listen. But for those who are not, then please let me know if you're lost at any point. Let's see, I saw something about sugars. Okay, so for sugars, well, that is something that was covered in the final, which I did not prepare for. So I think Dr. Melina is actually gonna do that tomorrow night if you register with her. I don't know how she does her registrations, but if you guys, I don't know if you guys know about Dr. Yeah, there's one more tomorrow. I think Dr. Melina was saying that she was gonna do one more, right? Because what we discussed was that I would focus heavily on alpha carbon chemistry, and she would do like the sugars, the amines, and the amino acids and stuff like that. So I will yeah. So because we kind of saw that like there's a lot of things to cover, so we want to break it down to 2 different days. So if you want to go Dr. Nina's review on sugars tomorrow, then I will just forward the list to her. In fact, yeah, I'll just forward the list to her, and I'll ask her to send you the link. Cool. All right. Sounds good. Okay. So let's talk about alpha carbon chemistry first, right? Like, can you tell me what are the typical reagents used to get this product? Whoa. Tell me what are some ways you could see it. The more substituted. This is known as what? Is this a thermodynamic or the kinetic? No, I'm only asking for the one I circle in pink. Is that a thermal or a kinetic? Good. Okay, so we know we're working with a thermodynamic enolate, which is more substituted. So we're going to have stuff like potassium hydride in 18 crown 6, right? Naomi does a job as well. Naomi and her homies. Remember what she does in the one? She's coming back to haunt you in Argo too. Potassium. Okay, so I don't like using potassium terbutoxide because it's really disputed right now. So don't use that. Use LDA as well. You can use LDA to how many equivalents? 0.95 or 1.05. Oh yeah. So yeah, Naomi and her homies is one of the reagents I introduced to my Orgo 1 students as well. So it's a small base, right? Oh, sorry. Hang on. Let me just share the. I know. Give me 1 second. Okay, it's back on. Right. So Naomi and her homies in 0.95 equivalents or 1.05 equivalents. Are you sure for this enolate you're gonna use 1.05? Oh, sorry, not for Naomi and her homies. I meant LDA. I didn't write it yet. There we go. There we go. So LDA. Yes, there we go. So now LDA and THF, we are going to have to use 0.95 equivalents, right? So for the thermodynamic one, can you guys tell me what other variations you would probably see? You're going to see LDA in 1.05 equivalents? Anything else? Yeah, you could use any HDMF here as well. It's usually only that, right? It's not a lot of options for that. Okay, because I don't know, we probably don't work with that a lot. So good job, you guys identified the reagents. So be careful of subtle things like that. Okay, if you had this material, for example, right, and I send it through LDA, what's going to happen is that it's going to deprotonate, right? Let me draw the hydrogen here. Okay, and then forms the enolate to give me this here. Then this acts as a good nucleophile and attacks the electrophile. Oops, 1.05. Good job. Okay, so then this goes down here. And then the double bond is a good nucleophile and attacks, kicks it off here. Right. Also, sorry, I'm missing a carbon here. That's why it doesn't seem right. No, we are correct. So we get our product from there, which is this product here. Okay, so we just added an R group. So this is considered the easy stuff, right? Because if you get this, well, that would be nice, but I doubt you are going to work with something that easy. Okay, but this is just sort of like easing you into enolate chemistry. It was one of the first few reactions that you learned. All right. Okay, let's look at another example. Same thing. What happens here? LDA, which is lithium diisopropyl amide, right? It's gonna deprotonate the hydrogen right here to give me my enolate. And then if I have an aldehyde, oh, so when you see aldehydes, you kind of know that it's an aldehyde condensation already. But because this is just a really simple one, so I mean, we don't really have to care about the stereochemistry yet, right? Then I get this. And then the last step is just an acidic workup. Grab a proton here, and then what I finish it off with is my final product here. All right, so then now if I start working with more complicated molecules, stuff like the one you see at the bottom, right? You have to start taking into consideration the R groups that are next to it, okay? So let's look at this right here. I have phenyl, I have tert-butyl. Are they big or small R groups? Big, right? Anything else that you see, such as amines as well, and R2 of some sorts, they are also considered big. So big R groups, right? They generate what kind of enolates? A Z enolate, very good. And when you have a Z enolate generated, your final product is going to be syn, okay? And that's what you're going to see in a little bit. But right now, I'm just going to go ahead and circle this here. Okay, so these are considered big components here. Big. Okay, which means that whatever you see on the other side here are small, right? So these are small. And therefore, they generate E-enolates, which means I get anti-product. Okay, usually other variations of small enolates that can form are from what? Ethers, thiols, and of course your usual ethyl, methyl, blah, 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 so on and so forth, right? So these are all really, really small groups. Okay, how I remember it as a student was using the acronym SEA, because when you have a small alkene, a small R group, you generate an E enolate and you get an anti-product. Okay, so if you kind of like forget how to do it, just remember C. So we're going to talk about the stereoselectivity for autocondensates. So let's start off with this example here. I've given you the outline of the reaction, but what you need to do is to show me the transition states, right? So we know what's going to happen here. Let me just write it out for you. Okay, so the first thing that happens is it's going to deprotonate your alpha carbon hydrogen. to give me this. Right? And then this forms transition state 1. And then after I can, because now I know that it's a Z enolate, right? I will get this product here. No, let me not do it here so that you guys can see it a little bit better. Okay. Okay, there we go. Right, so I get my Z enolate. And then what happens is that I will find the aldehyde. So remember, aldyl condensations, you would have to use an aldehyde. Okay, the whole point of doing this is to look out for the aldehyde here. Okay, it's gonna find it. I have a methyl right here. Okay, and then it's gonna do its nucleophilic attack. Hit transition state 2. Okay, to give me this product here. What I have here is a phenyl and the I have the nucleophile here, right? And then I just got to do an acidic workup to deprotonate this proton here. So what I get as a final product is a syn product, right? Because we had a Z alkene, right? So that was a big R group, Z alkene, and therefore a syn product. You could write the enantiomer as well. That's fine. Okay, so what I want to focus on right now is the two transition states you see here, transition state 1, okay, and transition state 2. These two are fundamental in getting you the points. Usually, I don't know if you guys saw a practice exam. They had one question on it, right? So I guess it's pretty important that you know what's going on. And right now I'm going to do an example. Okay, so let's talk about transition state 1. Same thing here. Okay, so the first transition state, I'm going to use a bit of a bolder marker. I have this. Okay, so this is isopropyl, and yeah, okay, so this is my first transition state here, the one where we determine whether we get an E or Z alkene, right? So follow my highlighters. I have this bond here in purple, and then I have an R group, right? So okay, this bond in purple It's going to be the bond right here. Okay, keep track with me. All right, so we want to generate a Z alkene. When we do that, you can ask yourself, okay, what happens if I put the phenyl here versus if I put the phenyl here, right? When you put the phenyl, the blues on the blue side, what do you think is going to happen? Yeah, it's gonna be, that's a really strong steric hindrance here, right? Can you see that? So two bulky groups together, then there's gonna be a lot of steric interaction, and that's not a good thing. So it has no choice but to go on to the other side, right? So when it goes onto the other side, this is exactly why we have an E alkene, sorry, a Z alkene, because right here, this bond here, you see they're on the same phase, and this is how we get our product, okay? So that is the first transition state. And then of course, I mean, you guys should know that right here is just a hydrogen, right? So can you see how I'm drawing the transition states right now? Are you guys able to see the link between where the bonds are? Let me not put this there. I'm just gonna do this. Okay, awesome. So because my phenyl and my oxygen are in the same phase, they are syn. All right, now after I go through the second nucleophilic attack, I'm gonna get transition state 2, right? And this is the one with the big chair again. Right here, and okay. Always remember that on the right-hand side of the chair, which is, okay, let me use a different color, which is this side here, we are talking about the aldehyde phase. And then the one on the left of the chair in orange, okay, this is the enolate phase. Okay, so what does this mean? Everything that is on this side should come from your aldehyde. And in our case, our aldehyde is the toluene molecule here, right? So, okay, you will probably get, if you get a question, you have to like label where the thing goes. Okay, can you guys tell me what position? I hope you guys remember your Orgo 1 when we talk about chairs. Each substituent can either be axial or equatorial, right? Can you tell me which is the axial position? The circle, exactly. So when you have axial positions, typically, would you want to put a lot of weight on it? Do you think it's a good thing? No, the molecule's not happy, right? Like us humans, nature is lazy. So it doesn't want to put the heaviest stuff on the axial position. And this is why the hydrogen atom from the aldehyde will always be on the axial position. Okay, let me remind you that no matter the case, every single point. So if you guys are like freaking on your algo exam, the first thing you want to do is to turn to that page where you see this chair and put the hydrogen on the axial position. Okay, I'm gonna yell at this a lot. All right, it will always be facing down, which means that you kind of solve the aldehyde phase, right? So you know that the other phase has to, the other substituent has to be my benzene right here. Okay, so we have done the aldehyde phase. Now we have to settle the enolate phase, correct? Okay, so for the enolate phase, it's a little bit different as what you saw from the previous transition state. What happens now is that, okay, the bond in green that I had previously is now going to be right here. Okay, this is the bond in green, which means I need to draw a substituent down. Okay, and then the bond in purple is going to end up here. Oh, sorry, down. Okay, because it's down. So this here would be the phenyl group. But wait, am I drawing it correctly? No, right? Because I need to make a syn product. So when it's a syn product, they're both on the same face, and exactly green should be up, right? Dr. Molina like saying what? Checking to see if you are paying attention, right? So be really careful about stuff like that. So the phenyl goes here, the phenyl and propyl goes here, and then you have your aldehyde and your R group. Okay? Let me write a note here to say that this hydrogen is always axial. Any questions about the Zimmermann Traxler so far? You guys doing okay? Okay, so that sounds good. Good. I'm glad you guys are getting it. Okay, let me show you what I did on my exam. Okay, so same thing. I said that, okay, I just told you that it has to be axial, right? The hydrogen, look at what I did. I put the phenyl on the axial position. So please don't do that. And you know what the best part was that I could say that H is always axial, and look at where it ended up at. Okay, yeah. So don't pull off an Ian when you're on the exam. When you get to this question, please kind of like remember. Okay, yeah, and exactly that's what I did. I learned from my mistakes, and look at where I am right now, helping you guys prepare for your exam tomorrow. So everything here is wrong, by the way. So don't look at there. Okay. I'm gonna do similar examples. Don't use those. Those are not good examples to work off of. Okay. Now I have more examples. So let's try them. And don't worry, in the exam they will give you the chair if they ask you a question like that. Okay. So dimethylamine. Big or small? Good. Okay, so you know it's a big. So write out your thoughts first. It's a big group, and then what happens? I'm going to generate an E or Z alkene. Z, and therefore I get N. Okay, good. So let me draw the template. Right here, IPR, and okay. So let's fill in the gaps here, right? I'm going to use different colors, and you're going to tell me what goes where. Okay, So I have a blue, a green, and a pink. Can you tell me what groups go where? Okay, good. So the blue one is NME2. No, Ariel. Remember, this is the first transition state right here. So first transition state, we have not touched any of the aldehydes yet. Right, we're still working with our studying material, which is the dimethylamine here, right? And then I have this here, right? So what do you think the ethyl is? Well, at the end of the day, because we have a big group, so we are gonna get a Z alkene. Where would I put my ethyl such that I get the Z alkene? Here or here? The one on the left, right? This is where I get my Z alkene here. So I know ethyl has to be here. Which leaves the last one to be just a hydrogen. Okay. Good. So this is the first transition state. All right, the second transition state. Now we can talk about the aldehyde phase. Okay. So which is the aldehyde phase? The left or the right hand side of the chair? Can you tell me what goes on the orange bond? Yeah, I hope that nightmare of my exam kind of flashes in your head. Good. Hydrogen is always axial, right? So which means that the other position has to be terbutyl. There's no other thing. So you see how easy it is to just get points here on the exam, right? Okay, now let's talk about the enolate phase. This is usually where students have trouble. So the first thing you want to do every time you struggle is to take a marker with you, or a colored pencil or crayon, something that's of a different color that helps you see. What I would do is to do this. So I know I need a Z alkene, right? So this would give me my Z alkene, which means my ethyl has to be here. Once you get that out of the way, everything else will fall into place. Okay, so for example, what else do I have left? I have my dimethylamine, which is going to point down. And there you go. The last thing that I need to add here is probably just a hydrogen. Okay, so don't worry, I'll upload these slides after the review, so you can continue looking at it if you're still lost. Also, don't forget I'm doing a lecture capture right now. I will send you the link together with the review slides. Okay, let's try a small example. So I have this. As you can see, I'm using a thiol. Thiol with LDA. Okay, and this gives me transition state 1. Am I going to get a E or a Z, right? Small e, anti, so C. So it's going to be this, and 1, 2. Sorry, made a mistake here. Okay, so now I get my anti-alkene, just to verify that yes, this is anti. Okay, now I'm gonna add my aldehyde. Now remember, aldehyde condensation is all about enolates with aldehydes. Transition state 2 to give me this product here. What goes here would be the phenyl, and then my carbonyl and the isopropyl. Okay, so we know that it's going to be a small and we are going to get an E-enolate and we get an anti-product, right? Okay, so let me draw you the chair. All right, now tell me what goes on the red bond. No, it's the thiol. Okay, it's the thiol. Because it's the one that's right here. There you go. Good job. Now, tell me what goes on the orange bond here. Good. Phenyl, and then of course the last one then have to be hydrogen, right? Now, double check your work. You have a small group here, and you have this. So the interaction is not that bad, right? So that's why we can generate the E-alkene. So make sure you have that here. Okay, I'm gonna highlight this for you in gray, so you know that we are working with an E-alkene. Okay, next thing, when we talk about transition state 2, let's see, we have this here, and we have this here. So now, okay, good. So this is our transition state 2. Again, just because it's a small enolate that I'm working with, does it change the position of the hydrogen here? Do I still put a hydrogen? Yeah, it doesn't change, right? So hydrogen will always be there, which means what's my other R group now? The one that I'm missing. Isopropyl. Excellent. Okay. And then tell me what goes on here. Okay, let me draw it out. Right here. What goes here? The thiol. Good. Which means that because at the end of the day, remember we want an anti-product. So if I don't know, remember if you get lost, draw the the E-alkene. So you know that this bond here has to go down, okay, with your phenyl. Which means that everything here is just hydrogen. Okay, so this is transition state 2. Okay, so just to recap, whatever you see here is the enolate. Whatever you see here is the aldehyde. Okay, I left one more example for you to go and try it on your own. You can just follow what I did here in your own free time. All right. Yeah, you will put ammonium chloride. You can put water. You can put acid. I just didn't put it here. But yes, if you are asked to predict the reagents, don't forget the last step. Because what I'm trying to do here is just to focus purely on the transition states. Okay, so there are more examples of alpha carbon chemistry. You might get an example where you have multiple alpha carbons, and then you have to exercise your judgment to decide where is Naomi gonna attack, right? So I have at this point here 3 alpha carbons, right? Or 3 different spots that I can deprotonate. Can you guys see that? I feel like Dora the Explorer right now. Can you tell me where the alpha carbons are? You know that clicking sound that she has here? Let me use a different color. Okay, I have 1 here. I have 1 here, alpha prime, and 1 more here, right? So where would I deprotonate? Since I have 3, do I just like throw a dice tomorrow? Okay, so this is let me write it down. So in the event you have multiple alpha carbons, find the one that gives me the most number of rings. Okay, what does this mean is that now if I deprotonated this hydrogen here, the yellow one, right? I will get how many rings? How many rings can I form with this ketone? 1, 2, 3. It's and then I will have a 4-membered ring. It's bad, right? It's not as good. So the alpha double prime, I'm just gonna keep track here. So alpha double prime, 4-membered ring. Okay, what about alpha prime? The first one. Right here. Right? If I deprotonate here, then what's gonna happen is I get 1, 3, also 4-membered ring. So is it good? There's quite a lot of green, right? But what if I just protonated alpha? I would get, well, let's see, 1, 2, 3, 4, 5 memory. Wow. So which is the most stable one? It's this one here. Okay, this is the 5-membered ring. So we would deprotonate the one at the very end of the ketone. Okay, so let's look at the mechanism for that. Okay, we have this hydrogen here, H2C. Right, so Naomi and her homies, please remember that she is a reversible process, right? Okay, so it's not the end of the world if you forget that it's a reversible process, but every time you see Naomi, just remember to keep putting on the double arrows until you get to the part where you finally finish off the product. Then, or usually when you're going to write heat, that's where you kind of make it one directional. Okay, so OME, right? Naomi's going to come in and deprotonate this hydrogen, and then it's going to form a double bond, or rather an enol, to give me this. Okay, now this is going to be a good nucleophile, and it's going to go straight for the aldehyde. Okay, and I get a 5-membered ring. Right here. And what I also have is, well, because I knocked out the aldehyde, right? I'm going to get this right here. Okay. Now, this is a good nucleophile, right? So it's going to, what do you think its first instinct is going to do? It's going to deprotonate this hydrogen here. And what's going to happen is that you're going to form an enolate again. Because remember, this is the whole reaction mechanism is just a formation of different enolates until you get until you can't do it anymore, right? So right here, and then I get alcohol. And then what's going to happen after is that, well, the same thing, right? I'm going to form back my ketone. This double bond comes out here, and under basic conditions, well, alcohols can leave. You can kick them out. So I have an alkene here, and this ketone, right? Oh, sorry, this is the last step. So it's done. Okay. So go and take note of this mechanism because it's pretty important. But what you need to remember is that the alpha carbon is the one that gives you the most number of rings. All right. This is also another really popular reaction. You might see it hiding in the form of a predictive product kind of problem, but usually for this, you need to, at least for me, I like drawing out the mechanism just to be able to see what's going on. Okay, and there are a few things that you need to remember for this. There's a few driving forces, okay? First thing to look out for is that you have a 1,3-diketone and you have a methyl vinyl ketone. Okay, so this is a methyl vinyl ketone and this is a 1,3-diketone. When you see these two coming together, the first thing you want to think of is, all right, I am gonna get a Robinson annulation, which is this product that you see on the right. Okay, and they might switch up substituents like that, you know, just to throw you off, but just focus on the bare skeleton and then fill in the structures on later. Okay, usually Robinson annulation is the one that kind of like kills people because it's so good at hiding. It's really subtle as well, right? So, all right, you're gonna use Naomi and her homie, same deal, right? But in this case, you know which is the alpha carbon, correct? I'm hoping you guys do that. Do know that, which is the one right here in between the two carbonyls. So she's gonna come in and deprotonate this, right? What happens after is, remember, reversible process. You get an enolate. Okay, and then this enolate is going to now attack the other substituent, the methyl vinyl ketone. Forms a double bond here. And then this now becomes a good nucleophile. Oh, sorry. And go straight for the double bond here. Okay, why? Because when I attack this site, I can form an enolate, right? So remember, you have to keep forming enolates at this step. If all of a sudden you see that, oh, before adding heat, you don't see an enolate anymore, you're probably doing it wrong. Okay, so now I have my 1,3-diketone back, and what I get is this product here. Okay, so let me label out the carbons for you, just so you know what's going on. Okay, this carbon here is right here. This carbon is the one here. And then this carbon here is the one right here. This carbon right here is the one here. Okay, so this is what you're forming. All right, are we done? No, because we are still at, we have not finished our product yet, right? Remember, we need to form a ring, and how do we do that? Right now, I can't form this ring here, because if I form a ring here, I'm not gonna get a 6-member ring. I'm gonna probably get 5, right? And with the methyl sticking out, so I cannot attack at this point. Because BC means because it will give me 5-member ring, MR, okay? So what's going to happen right now is that there is a proton transfer to give the kinetic enolate. So this is one of the driving forces that you need to remember for this reaction. And it's just a proton transfer, so I end up with the kinetic enolate here. Okay, this is a driving force. And then now this this enolate, now if I form back my double bond, is going to give me my 6-member ring, the one that I wanted originally, right? So now it's going to go here and attack here. Okay, and what I get is now 6-member rings here. So I have, well, this doesn't change, right? But then this now becomes an alkoxy group, and then what I have is a double bond here. Okay. So remember, every time you see this happening, you have to look for the nearest hydrogen, right? The hydrogen that would give you an enolate. So same thing, grabs a hydrogen here so that it forms a double bond and picks off this bond here. Okay, because you have a loss of a hydride group already, so it's no longer reversible. What you get is this right here with an OH and a double bond. See, notice how at every step I have an enolate of sorts. That's how I know I'm doing it right. Okay, and then this is the last step when you're going to put heat to stop the reaction from going backwards, right? So this forms a double bond, right? And then this double bond gets moved over here, kicks off the alcohol. So in essence, this is where I get my product. Right here, and carbonyl here, carbonyl here. Boom. Okay, any questions here? All right, seems you guys are understanding what's going on here. That's good. Wow, different semesters have a different needs for sure. Because I'm not in your classes, so I don't know what you guys are struggling with typically. But with that, let's go back to. We can go back to this question now. Where is it? Right here, right? So this is why I wanted to put this for later, because I wanted you guys to be familiar with what was going on first. So what tells me that this is probably a Robinson annulation? Can you see what are the trends here? I have a 1,3 diketone, so I should be looking out for a methyl vinyl ketone, which is right here. So okay. But let me go stepwise first so that you know what's going on. Naomi is going to deprotonate hydrogen here. So, okay, just draw my enolate. Right, and then, oh, I just have a addition here. So I know that I'm going to get this product. And just N-propyl with my ketone here. Okay, and then Naomi is going to come in again, right, to deprotonate this one here. So now I have this step 3, step 2, step 1, okay, and then what am I going to get? Do you guys go through the mechanism for this, or can I just write out the answer and you guys want to figure it out yourselves? Which do you guys prefer? Yoo-hoo. If no one has comments, and I'm just going to write the answer, and you guys can probably figure out the mechanism on your own, right? Okay, that's fine. So the answer is this right here. Okay, and then the N-propyl is here, and then I have a methyl here. So go figure out the mechanism. If you are lost, feel free to let me know. With that, this is my review for enolate chemistry for you guys. I hope I kind of help you learn something today. I'm going to cut off the lecture capture right here to answer questions.